Good morning, students. Spin-spin coupling is the important part of NMR spectroscopy. Deuterium coupling with carbon and deuterium coupling with proton is an interesting topic in NMR spectroscopy. This is because deuterium and proton, even though they are isotopes one another, they do not have same spin quantum number. Proton has spin quantum number half, while deuterium has spin quantum number 1. Therefore, the splitting pattern and the line intensity for deuterium and proton are different. Carbon deuterium coupling is determined by the formula 2Ni plus 1, where I is the spin quantum number of deuterium and N is the number of deuteriums attached to that carbon atom. While carbon proton coupling follows the rule of N plus 1 rule, where N is the number of protons attached to that carbon atom itself. Okay, according to that, carbon atom, if it is attached to one proton, it gives a doublet, N plus 1 rule. If it is attached to two protons, it gives a triplet, and if it is attached to three protons, the carbon atom gives the quartet. But if deuterium is present, then the splitting pattern is little bit different than proton coupling. For example, if one carbon atom is there and it is not having any proton or any deuterium attached to it, it will give the single line splitting pattern, or single line is observed. If one deuterium is attached to the carbon atom, then we get the three lines of intensity 1 is to 1 is to 1, that is equal intensity line triplet is observed. If I put n is equal to 1 here, I will get 2 into 1 into 1 plus 1 3, that is three line splitting pattern will be there with equal intensity. If two deuteriums are attached to carbon atom, then we get a quintet with 1 is to 2 is to 3 is to 2 is to 1 line intensity. So depending on number of deuteriums attached, we get different number of lines for carbon spectrum or carbon signal. So this table shows the number of deuteriums attached to the carbon atom, number of lines in the signal, and this is the intensity pattern. Intensity pattern can be easily remembered if I'm having one deuterium attached to it. Its signal intensity is 1 is to 1 is to 1. We have to remember this intensity pattern only. Now if I'm having two deuteriums, how will I will remember? This one is always one for each signal. Then I have to add the 1 plus 1, the previous signal intensities we have to add 1 plus 1 2. Then we have to add all the three intensities of previous signal 1 plus 1 plus 1 3. So 1 is to 2 is to 3. Again I have to skip the first line intensity and just add the next two, 1 plus 1 2, so it is 2, and the last one is 1. So this is how we get the quintet for two deuteriums attached, or if the carbon atom with two deuteriums. Then if we have three deuteriums attached to the carbon atom, we get a septet, and the septet intensities are like this. So how can we get this? So first one is as it is, then this 1 plus 2 will get 3, then 1 plus 2 plus 3, it is 6. Then I have to skip this, and then we have to add a 2 plus 3 5, 5 plus 2 7. So this is the 7. So just by skipping first line intensity, I'll add 3 of these. Then skip the first as well as second, then add 3 plus 2 5 and plus 1 6, it is 6. Then what I have to do, I have to skip this third one and just 2 plus 1 3, and the last one will be 1 as it is. So this is how we can get the signal intensities. Now I will check for the next signal with four deuterium atoms. Then it is seen that there are 9 lines in the carbon spectrum. Look at this. The first is 1 as it is. 1 plus 3, 4. 1 plus 3, 4 plus 6, 10. Then I have to skip this. Just add 3 plus 6 and plus 7. So it is 16. So look at this, 16 is there. Skip then third one also. 6 plus 7, 13, and 13 plus 6, that is for next line intensity I have to add these three, so it is 19 signal intensity. Then skip the third one also. 7 plus 6, 13, and 13 plus 3, so this is the next 16. Then skip this and plus add 6 plus 3 plus 1, it is 10, so this is our 10. Then skip this and add these two. 3 plus 1, 4. And lastly, I have to write 1 as it is. So this is how we can get the signal intensities for all the situations without writing the spin orientations of different nuclei. So this is the next signal, which is having 5 deuteriums attached to carbon atom. It gives me 11 line pattern with this line intensity, while you can check it for 6 deuteriums with showing 13 lines with the line intensity 1 is to 6 is to 21, and so on. Now we can see some examples here. This is acetone D6, that is all the hydrogens of acetone are replaced by deuterium. In carbon spectrum of this compound acetone D6, the signal of this deuterated methyl group. Both the methyl groups are identical, therefore they show only one signal, and the multiplicity is 2Ni plus 1, 2 into 3 into 1, that is it becomes 6 plus this one 7, that is we get a septate. So see, deuterated acetone shows a septate, but when acetone is deuterated, some impurity of this acetone D5 remains always with this acetone, or sometimes it remains with deuterated acetone. The spectrum of this acetone D5 is very interesting in carbon 13 as well as in proton spectrum also. Proton spectrum is as usual proton spectrum of acetone D5. Proton spectrum means the this proton attached to this carbon atom. If I take its proton NMR, it will show the coupling with these two deuteriums. So this deuterium spin splitting is according to this 2Ni plus 1. So here N is 2 because two deuteriums are attached there. So 2 into 2, 4, 4 into 1, 4 plus 1, 5. So quintet. This means that this proton in its NMR will show quintet. It will show quintet. But it is very interesting that the carbon atom in the C13 spectrum, its C13 spectrum is very interesting. The multiplicity of such type of the nuclei where it is attached to two different nuclei, different in the sense their spin quantum numbers are different, then the multiplicity follows 2NaI plus 1 into 2NbI plus 1, where Na is one type of the nucleus and Nb is the second type of the nucleus. So let us consider in this example, one proton is attached. So this 2 into 1, one proton into half is the spin quantum number of proton plus 1. So it becomes 2. And there are two deuteriums attached to the carbon atom. So 2 into 2 into 1 plus 1, it is 5. And this 2 into 5, it becomes 10. So this carbon atom in C13 spectrum, not in the proton spectrum, in the C13 spectrum shows 10 lines. So this means that proton and deuterium, they couple separately with the carbon atom. This is how we can get the signal intensities and number of lines in various deuterated compounds. Now let us see some spin orientations of deuteriums with respect to carbon atom. Before that, see some facts related to this. CD3Cl, that is deuterated methyl chloride, shows 7 lines of unequal intensity in CMR spectrum, while CdCl3, that is deuterated chloroform, shows a triplet of intensities 1:1:1 in CMR spectrum. And this is dimethyl sulfoxide, deuterated dimethyl sulfoxide, DMSO D6. It shows 5 lines in CMR spectrum at 40.1 ppm. Such type of the questions are asked in your university question papers. Now we'll see spin orientations of deuterium with respect to carbons. That is now carbon deuterium coupling and the different spin orientations of the deuterium. As deuterium has spin quantum number I is equal to 1, it will have 2i plus 1 different spin orientation. It's 2i plus 1 means there are 3 different spin orientation. That is, one deuterium atom can have 3 different spin orientation. What are those 3 different spin orientation? -1, 0, and +1. These are the 3 different spin orientations of the deuterium. -1 is this. The nuclear spin of the deuterium is parallel to the applied magnetic field. This will be the applied magnetic field, B0. Then the nucleus will have 0 spin orientation. That is, it is represented by dot, and it will have +1 spin state. That is, it is in the opposite direction to the applied magnetic field. So these are the different orientations possible for one deuterium. This is the reason, that is, all the 3 orientations of deuterium are equally possible, and therefore a compound which is having one deuterium attached to carbon atom shows a triplet. 3 lines are there with equal intensity. For example, CdCl3, that is deuterated chloroform, shows a equal intensity triplet in the CMR spectrum at 77 ppm. Always you will see the solvent peak at 77, these 3 equal line intensities for CdCl3. Now, if there are 2 deuteriums attached to the carbon atom, then these deuteriums can take different orientations. What are those different orientations? Look at this. This is -2, -1, 0, +1, and +2. That is -2 to +2. Total 5 different orientations these 2 deuteriums can take. What are those 2 deuteriums? +2 orientation means both the deuteriums will have their spins opposite to the applied magnetic field, while -2 means both the deuteriums will have their spins parallel to the applied magnetic field. Then we'll have +1 spin orientation. +1 spin orientation means one of the deuterium will have its spin orientation opposite to the applied magnetic field. That is, it is in +1 spin orientation, while the other one will have 0 spin orientation. And these are two equally possible. These two possibilities are equal. That is, first one, this one of the nucleus is having 0 spin orientation, while at the second time the second nucleus will have 0 spin orientation. So these two possibilities are equally possible. Then the 0 spin orientation means one of the deuterium has spin orientation parallel to the applied magnetic field, while other will have opposite to the applied magnetic field. And this type of the possibilities, there are two possibilities, while the third possibility is that both the nuclei will have 0 spin orientations. So there are 3 possibilities of 0 spin orientation. Then we have -1 spin orientation also. So now if you check the spin orientations and their possibilities, so the possibilities are in the ratio of 1:2:3:2:1. So therefore it will give me a quintet with the line intensity of 1:2:3:2:1. And this is the situation where there are three deuteriums attached, that is like just acetone D6. There are three deuteriums attached to the carbon atom. These three deuteriums can have different spin orientations with respect to the carbon atom. Firstly, if you see what are those spin orientation, it is -3, -2, -1, 0 to +1, +2 and +3. Total 7 different spin states are possible for all the three deuteriums. So if you look at this, you will notice that in one case all the three nuclei will be having their spin orientations parallel to the applied magnetic field, while in other case they will be having their spin orientation opposite to the applied magnetic field. This is only one possibility for these two spin orientations. And now we have other spin orientations also, where we have +2, that is two nuclei are having opposite orientation, while one will be having zero spin orientation. +1 means one is having opposite spin orientation while other two make it zero. For example, in this case, look at this. These two cancel one another and they become zero, and only one is there, so it is +1 spin orientation. In this case, you will notice that these two are cancelling one another and this is +1 orientation. But if you look at this, the nuclei have interchanged their orientations. Again, these two cancel one another and this one will be having +1 orientation. And now look at these three possibilities with two nuclei having zero spin orientation and one nucleus with +1 spin orientation. So you will check that all these 6 possibilities are of +1 spin orientation. Net result of this orientation is +1. And this is the next possibility, where the three nuclei will have zero spin orientation. Out of this, look at this first possibility. Two nuclei cancel one another's spin orientation, and while the third nucleus is having zero spin orientation. Now, if you check all the possibilities, you will notice that these possibilities or these combinations of spin orientation lead to the zero spin orientation. And so there are total 7 possibilities, and the line intents, that is possibility, this first possibility is only having one possible orientation for all the three nuclei. Then the line intensities depend on this type of the spin orientation, and which is observed in the ratio of 1:3:6:7:6:3:1. So this is how the carbon deuterium coupling will show different signal intensities than the proton signal intensities. Let us stop here, and in the next lecture we'll see the